Standing at the edge of a high desert ridge in the dead of January, the air does not just blow against your face. It cuts like shattered glass. The wind is screaming across the open mesa at 40 miles per hour, driving the surface temperature down to a brutal minus 15 degrees Fahrenheit. Everything above ground is frozen solid. Trees snapping under ice, power lines humming under tension, and every conventional house on the horizon hemorrhaging heat into the sky. But step back 3 feet and look straight down into the dirt. You are staring into a 12-foot deep subterranean pit, carved directly out of the frozen clay and lined with raw concrete walls. Up here on the surface, you cannot stand still for 30 seconds without frostbite biting through your gloves. Down there, inside that sunken courtyard, there is no wind, no draft, not even a ripple in a standing glass of water. When you point a thermal imaging camera down into that hole, something deeply unnatural happens on the display screen. The surrounding prairie glows in deep, icy cobalt blue, registering near sub-zero surface temperatures. But the bottom of that pit, surrounded by thousands of tons of raw earth, glows in a soft, radiant orange. When local construction crews first watched the owner dig this hole in 1978, they laughed out loud. They called it a waste of land, a $40,000 bathtub, and a death trap that would fill with ice and mud the very first time a winter storm rolled over the mountains. They were convinced the raw pressure of the earth would snap those retaining walls like dry twigs. Then came the historic freeze, a polar vortex that knocked out power to over 10,000 homes across the county for 4 straight days. While families above ground watched their water pipes burst inside their walls, this sunken courtyard did something extraordinary. Without a single watt of electricity from the grid, without an electric furnace or a gas line, the living space tucked behind that sunken courtyard held a steady, unwavering 68 degrees Fahrenheit. The cold air was caught, trapped, and neutralized before it could ever touch the front door. If you are interested in real-world off-grid engineering, passive thermal survival, and learning how to build structures that outlast the electrical grid, take a quick moment right now to hit the subscribe button down below. And while you are down there, drop a quick comment with your city and your current outdoor temperature right now. I want to see exactly where across the country you are watching from today. To understand why a simple excavation in the dirt can outsmart $100,000 worth of modern heating equipment, you have to understand the cruel illusion of standard American home construction. In places like the high plateau of Taos, New Mexico, or the frozen plains of northern Arizona, the weather plays a brutal, deceptive game. During the afternoon, the high desert sun beams through thin air, warming the dirt to a pleasant 60 degrees. But the moment that sun dips below the horizon, the sky turns into a giant, heat-sucking vacuum. Nocturnal radiational cooling takes over, and the temperature plummets 30, 40, sometimes 45 degrees in a matter of hours. Most modern homes are built to fight this relentless cycle using light timber framing, 2x4 wooden studs, thin sheets of drywall, and a pink blanket of fiberglass insulation battings rated at R13. Now, picture this. A standard stick-framed house does not actually store heat. It merely slows down the rate at which heat escapes. It is an insulated cardboard box balanced on top of a frozen windy hill. The moment the electrical grid dies, or the propane delivery truck fails to arrive, that box begins to drain. Within 6 hours, the interior temperature drops into the 40-degree range. Within 18 hours, the cold air penetrates every wall cavity, freezing the copper plumbing lines until they split open like overpressurized soda cans. That exact scenario played out across the United States during the severe energy crises of 1973 and 1979, and again during the Great Grid collapses of 1977. Homes that cost hundreds of thousands of dollars became unlivable iceboxes in less than a day, forcing families to abandon their properties or burn their own furniture in open fireplaces just to stay alive. Back in the late 1970s, one independent builder decided he was done relying on thin wooden walls and high-maintenance heating systems. He stood on his wind-swept parcel of high desert land, watching the grass whip back and forth under a bitter north wind, and realized something fundamental about architectural history. For thousands of years, ancient builders in the arid regions of China, the Roman Empire, and the American Southwest did not build higher into the wind to keep warm. They dug down. Here's what everyone missed. The atmosphere above our heads is volatile, unstable, and subject to wild 40-degree temperature swings every single day. But the earth beneath our feet is entirely different. Once you dig down 10 to 20 feet into the soil, the earth reaches a constant, perpetual equilibrium. In most of the continental United States, the deep soil stays at a continuous 50 to 60 degrees Fahrenheit, 365 days a year. Regardless of whether there is a 100-degree heat wave or a sub-zero blizzard raging on the surface, the soil does not function as a high-performance insulator. Uninsulated dirt actually has a very low resistance to heat flow, carrying an R value of only 0.125 to 0.25 per inch. Instead, soil acts as a massive, high-density thermal flywheel. A single cubic yard of packed earth and clay weighs nearly 3,000 pounds, holding an immense capacity to store thermal energy. When you bury a structure or surround an outdoor courtyard with 12 feet of subterranean earth, you are no longer fighting the negative 15-degree atmospheric air. You are coupling your living space to a giant, stable, thermal battery that never drops below 50 degrees. When the builder brought in a 20-ton diesel excavator and began tearing open a massive, 12-foot deep pit in the middle of his property, the local community thought he had lost his mind. Neighbors drove by in their pickup trucks, staring down into the giant red clay crater. The local building inspector shook his head, warning him that heavy rain would turn the hole into a stagnant mud pit, and that the weight of the surrounding soil would exert hundreds of thousands of pounds of lateral force, pushing the walls inward until the entire structure collapsed. They warned him about soil expansion during winter freeze-thaw cycles, where wet clay expands with immense force, capable of shearing unreinforced concrete walls in half. They called his vision a waste of prime topsoil, a foolish experiment that ignored basic construction standards. What they did not understand was that he was not just digging a hole, he was engineering a subterranean microclimate designed to manipulate the laws of fluid air dynamics and thermal mass to capture free heat from the sky and shield his home from the deadliest winter winds on Earth. The excavation process was not a gentle operation. It was a violent, relentless battle against raw geology. Day after day, the heavy diesel engine of the 20-ton excavator roared against the silent high desert landscape. The steel bucket ground against stubborn layers of packed clay and embedded limestone, sending shuddering vibrations through the ground with every bite. With each scoop, hundreds of pounds of cold, damp soil were lifted from the earth and dumped into towering mounds along the perimeter. The smell of raw earth, crushed stone, and unburnt diesel exhaust hung heavy in the crisp morning air. As the machine dug deeper, passing 6 feet, 8 feet, then 10 feet below grade, the nature of the soil began to shift. The dry, dusty topsoil gave way to dense, cool, reddish-brown clay that felt almost cold to the touch even in the heat of midday. At a depth of exactly 12 feet, the excavator operator reached the target depth, carving out a wide, rectangular pit measuring 30 feet long by 20 feet wide. Standing at the bottom of that freshly dug earthen trench, looking up at 12-foot walls of raw clay, the physical change in environment was immediate. The biting wind that ripped across the surface was completely gone, replaced by a deep, heavy stillness. The earth walls felt cool and solid, holding a constant ground temperature of roughly 55 degrees Fahrenheit. But carving a giant hole in the ground is only the beginning, because an unreinforced earthen pit is a ticking structural clock. Think about that for a second. A 12-foot-high earth embankment exerts an immense amount of lateral pressure against anything built at its base. During wet weather, when rain saturates the surrounding soil, that earth becomes heavy, fluid, and unstable. A single cubic yard of wet clay weighs over 3,000 pounds. Spread across a 30-foot retaining wall, the soil surrounding that sunken courtyard was exerting over 150 tons of continuous pushing force. If you build a standard timber wall or an unreinforced block wall against that kind of earth load, the first heavy rain or winter freeze will push the structure inward until it snaps in half. To prevent a catastrophic wall failure, the construction required a 3-step heavy structural engineering plan. The first step was managing water, because hydrostatic pressure is the ultimate destroyer of underground walls. When water accumulates behind a subterranean wall without an escape route, the pressure builds until the concrete cracks. To solve this, workers lined the entire floor perimeter of the pit with a deep bed of crushed river stone, 8 inches thick. Embedded inside this gravel trench was a network of 4-inch perforated drainage pipe, sloped gently away from the foundation toward a lower natural drainage channel down the slope. Every inch of the raw earth walls was coated with a heavy liquid asphalt membrane, followed by a layer of dimpled high-density polyethylene drainage board. This created a continuous vertical air gap behind the wall, allowing any groundwater seeping through the soil to trickle harmlessly down into the gravel bed and drain away before it could ever build pressure against the structure. The second step was building the structural retaining barrier itself. Instead of lightweight wood, the walls surrounding the courtyard were constructed using 12-inch steel-reinforced concrete masonry units, tied directly into a massive, continuous poured concrete footing 2 feet wide and 12 inches deep. Vertical steel rebar rods were anchored into the concrete footing every 16 inches, running all the way up to the top of the 12-foot wall. Once the block walls were stacked, every single hollow core inside those concrete blocks was filled with high-slump structural grout. This turned the perimeter of the courtyard into a solid, monolithic wall of steel-reinforced stone, capable of resisting hundreds of tons of lateral soil pressure without flexing a fraction of an inch. The third step was positioning the thermal mass for maximum energy absorption. The long axis of the courtyard was oriented precisely along an east-west line, facing the high wall directly south toward the winter sun. During the cold months, when the sun sits low on the southern horizon, sunlight streams straight into the sunken courtyard, striking the thick concrete floor and southern-facing walls for 6 continuous hours. The dark concrete absorbs that intense solar radiation, soaking up heat energy like a dense thermal sponge. Because high-density concrete has a volumetric heat capacity of roughly 30 British thermal units per cubic foot for every degree of temperature rise, the walls store millions of British thermal units of raw heat during the day. Then, as night falls and surface temperatures plunge, those walls slowly re-radiate that heat back into the court, keeping the air inside the sunken basin decades warmer than the freezing gale blowing above. To ensure that heat was not lost back into the shallow surface earth, rigid extruded polystyrene insulation boards, 2 inches thick, were buried horizontally around the upper perimeter rim, creating a thermal umbrella that blocked surface frost while keeping the lower walls directly connected to the deep 55-degree earth. The depth-to-width ratio of the courtyard was calculated down to the inch. If the pit is made too deep and too narrow, sunlight never reaches the bottom floor, leaving the space in perpetual, damp shadow. If it is made too wide and too shallow, high winds swoop down into the basin, blowing away all the trapped heat. By setting the depth at 12 feet and the floor width at 20 feet, the builder achieved the ideal geometric balance, allowing deep winter sun penetration while creating a dead air zone that deflected 50-mile-per-hour winds right over the top of the pit. While the structural masonry created an indestructible shell, The true operational secret of a sunken courtyard lies in the invisible laws of fluid mechanics. Air does not sit still. It behaves like a liquid. Warm air is light and buoyant, carrying a density of roughly 1.20 kilograms per cubic meter at room temperature. Cold air is dense, heavy, and rigid, weighing approximately 1.29 kilograms per cubic meter, near freezing. Because cold air is heavier, it naturally slides down slopes, seeking the lowest possible elevation point on the landscape. This movement is known as katabatic airflow. When night falls on the high desert, the ground loses its heat rapidly to the clear night sky through radiational cooling. The air touching the frozen surface cools down instantly, becomes heavy, and begins to flow downhill like invisible water, tumbling over the lip of the sunken courtyard and settling into the floor of the pit. This creates a localized cold air pool. If left unmanaged, a sunken court can actually trap cold air, creating a stagnant frost pocket where temperatures plunge lower than the surrounding terrain. This phenomenon leads directly to the most critical life safety danger in subterranean architectural design. A sunken court is a closed atmospheric basin because it forms a depression in the earth. Heavy gases that are denser than ambient air fall into the pit and cannot escape. If you place a wood stove, a rocket mass heater, or any combustion heating appliance inside a subterranean living space attached to a sunken courtyard, you enter a life-or-death engineering scenario. When wood or fossil fuels burn, they produce carbon monoxide gas, an odorless, colorless, toxic compound that displaces oxygen in the bloodstream. Under normal circumstances, warm flue gases rise up a chimney because they are less dense than the cold outside air. However, inside a subterranean space surrounded by a stagnant cold air pool, the atmospheric pressure dynamic flips. The heavy, cold air sitting inside the courtyard sinks down, creating a localized high-pressure zone right outside the windows. If the indoor combustion appliance attempts to draw air from inside the room without a dedicated intake, it creates a negative pressure draft inside the house. The cold, dense air outside forces its way down the chimney flue, reversing the airflow. Instead of smoke and poisonous carbon monoxide rising out of the roof stack, the chimney backdrafts. Lethal carbon monoxide gas is forced backward out of the stove door, flooding directly into the living quarters. Because carbon monoxide settles into low-lying, unventilated basins, the entire subterranean home can transform into a silent gas chamber in less than 20 minutes, killing every occupant inside without warning. Let that sink in. This is why building a sunken courtyard house without precise life safety engineering is an extraordinary hazard. To prevent this invisible threat, the construction incorporated 3 mandatory safety protocols. First, an isolated, direct combustion air intake pipe was installed. A 6-inch, non-combustible galvanized steel duct was piped directly from an external air manifold above grade, running underground straight into the sealed firebox of the indoor heater. This meant the fire drew 100% of its oxygen from outside the sunken court, eliminating indoor negative pressure and completely preventing backdrafting regardless of how cold or stagnant the courtyard air became. Second, the exhaust chimney was engineered using strict vertical stack height dynamics. To overcome the micro-inversion layer created by the pit, the double-wall insulated stainless steel chimney flue was extended continuously upward, rising a minimum of 3 feet above the highest point of the surrounding earth rim. By adhering strictly to the 10-foot, 2-foot clearance rule, the top of the chimney was positioned out of the stagnant air pool and back into the natural pressure currents of the surface wind, ensuring a continuous, powerful upward draft that sucked smoke and toxic exhaust out of the building. Third, life safety telemetry was integrated into the building itself. Dual UL 2034 compliant carbon monoxide alarms were wired with battery backups, mounted at floor level and breathing height near the living quarters. These sensors continuously monitor ambient parts per million gas levels, guaranteeing immediate early warnings long before any accumulation can occur. Only when these fluid air dynamics and strict combustion safety protocols were fully integrated did the subterranean pit transform from a potential hazard into an indestructible, life-saving sanctuary. The true validation of any off-grid engineering design does not happen on a warm, sunny afternoon or on a computer simulation model. It happens when nature unleashes its absolute worst, and human infrastructure collapses around it. That moment came during the legendary winter storm of 1982, a massive, historic Arctic polar vortex that roared down from northern Canada and slammed directly into the high desert mesa. By late afternoon, the horizon had completely disappeared behind a wall of blinding white snow. The wind was not just blowing, it was screaming at 60 miles per hour, whipping loose snow into razor-sharp horizontal drifts that cut visibility down to zero. On the open prairie, the ambient air temperature plunged to minus 22 degrees Fahrenheit. When combined with the gale force wind shear, the effective wind chill index reached a lethal minus 45 degrees Fahrenheit. At those temperatures, exposed skin freezes in under 90 seconds, and diesel fuel begins to gel inside vehicle tanks. At 3 o'clock in the morning, under the crushing weight of ice accumulation and hurricane-force gusts, the main electrical transmission grid gave way. Substation transformers exploded across the region, with bright flashes of blue light, killing power to more than 10,000 homes across 3 counties. In conventional timber-framed houses across the valley, the crisis began immediately. As electric heat pumps cut out and propane furnaces lost their electronic ignition systems, the cold air began its relentless invasion. With 60-mile-per-hour winds pushing cold air directly through every tiny gap in door frames, window sashes, and attic vents, standard homes began losing heat at a rate of 5 degrees per hour. By hour 6 of the blackout, families were huddled in their living rooms, watching indoor wall thermometers plummet into the 30-degree range. By the second day, water lines buried inside exterior walls began to freeze and rupture, flooding basements with ice-cold water that froze solid within hours. Families were forced to evacuate, battling treacherous whiteout conditions on unplowed roads just to reach emergency warming shelters in town. But inside the earth-sheltered home, tucked behind that 12-foot sunken courtyard, the storm felt like a distant memory happening on another planet. When you stood inside the subterranean living area, the first thing that struck you was the complete, profound silence. Above ground, the wind was ripping shingles off roofs and snapping tree branches like toothpicks. Down inside the dirt, behind 12 inches of steel-reinforced concrete and millions of pounds of high-density soil, there was not a single sound. The wind shear was forced to jump directly over the 30-foot opening of the pit, leaving the air inside the sunken courtyard completely motionless. As the storm raged into its second day, a fascinating physical phenomenon occurred right above the courtyard opening. Driven by the swirling winds, snow began to accumulate along the upper perimeter trellises and retaining wall edges. Instead of filling the courtyard floor, the wind currents caused the snow to bridge across the upper rim, forming an overhang of dense, frozen snow along the perimeter. This snow overhang acted as a natural secondary insulation blanket, trapping a buffer layer of stationary air underneath it, and further reducing radiant heat loss from the courtyard floor into the open sky. Inside the living space, the builder checked his isolated combustion heater. Outside, atmospheric air pressures were surging wildly due to the gale force gusts whipping across the roofline. In a poorly engineered underground home, those pressure surges would have created violent pressure swings inside the house, blowing smoke back out of the stove door and filling the rooms with deadly carbon monoxide gas. Instead, because the stove drew its air from a dedicated, non-combustible intake duct buried deep in the ground, and because the stainless steel chimney stack rose 3 feet above the wind shear boundary layer above grade, the stove burned with a steady, bright amber flame. The draft remained perfectly stable, pulling fresh air in, burning the wood cleanly, and venting every trace of carbon monoxide high into the storm winds above the rim. While conventional houses upstairs were freezing solid, the massive concrete walls of the sunken court were busy doing their job. The millions of British thermal units of heat stored inside those thick masonry blocks during the sunny days of autumn were now slowly, continuously releasing their energy back into the living space. For 72 continuous hours of dark, sub-zero freeze, without a single watt of electricity from the grid, the indoor temperature never dropped below 66 degrees Fahrenheit. When the storm finally cleared on the fifth day, and the sun broke through the icy clouds, the builder stepped out onto the courtyard floor to take sensor readings. He pointed a digital laser thermometer at the various zones of the property, recording exact empirical data to prove what passive engineering had accomplished. The numbers don't lie. Up on the surface of the open field, the ambient air temperature was minus 18 degrees Fahrenheit. Inside the sunken courtyard floor, completely sheltered from the wind shear and warmed by the deep earth foundation, the ambient air temperature was holding at 42 degrees Fahrenheit. That meant the simple geometry of the pit had created a localized microclimate that was 60 degrees warmer than the gale force air standing just 12 feet above it. Inside the subterranean house itself, the living space temperature was resting at a comfortable 68 degrees Fahrenheit. Meanwhile, just half a mile down the road, a standard wooden-framed house sat completely abandoned. With an interior room temperature of 28 degrees Fahrenheit, its plumbing destroyed, and its drywall ruined by burst water lines. The mechanical physics behind this difference comes down to simple energy mathematics. In a conventional above-ground house, up to 70% of total winter heat loss is caused by wind infiltration air forced through structural seams by wind pressure and convective cooling, where cold air blowing across exterior walls strips heat away at an accelerated rate. By sinking the courtyard 12 feet into the ground, wind velocity at the house envelope was reduced to 0 miles per hour. By eliminating wind shear, the rate of structural heat loss dropped by over 60%. And by coupling three sides of the building directly to 55-degree subterranean earth, the thermal gradient between the inside air and the outside walls was reduced from an 80-degree gap down to a manageable 13-degree gap. The home did not require a giant, high-maintenance furnace to stay warm, because it simply refused to lose its heat in the first place. Building a sunken courtyard home is not merely about saving money on heating bills or collecting interesting temperature data during a blizzard. It represents a fundamental shift in how we think about human shelter and off-grid survival. For over a century, modern architectural design has relied on brute force. We build thin, cheap boxes out of lightweight wood and sheetrock, and then install massive, complex, energy-hungry mechanical systems to continuously blast heat or cold air into them. We assume the electrical grid will always stay on, that fossil fuels will always be cheap, and that the atmosphere will always remain predictable. When the grid fails, those houses cease to function as shelters and transform into cold, uninhabitable liabilities. Subterranean architecture takes the exact opposite approach. By aligning structure with the natural laws of thermodynamics, mass energy storage, and fluid air dynamics, we create shelters that work times with time's gravity and earth physics, instead of endlessly consuming energy to fight them. A properly engineered, earth-sheltered home does not care if the power grid dies for 4 hours or 4 months. It does not care if fuel trucks cannot make it up the mountain. It relies on the constant, quiet, eternal heat of the earth itself, standing as a permanent sanctuary against whatever weather rolls over the horizon. However, if you intend to take these passive principles and apply them to your own off-grid homestead or underground build, you must respect the physical forces involved. Subterranean construction is not a casual weekend DIY project. Carving a deep depression into the ground involves massive lateral soil pressures, complex hydrostatic water drainage requirements, and severe atmospheric hazards. Before moving a single shovel of dirt, you must consult with a licensed structural engineer and soil mechanics specialist in your local jurisdiction. You must ensure that retaining walls are calculated for local wet soil lateral loads, that multi-layer French drains and sump channels are installed to prevent water accumulation, and that all local building codes are strictly satisfied. Most importantly, you must never compromise on life safety. Any fuel-burning appliance installed in a subterranean or enclosed courtyard space must feature an isolated, direct combustion air intake, a continuous vertical exhaust chimney adhering strictly to the 10-foot, 2-foot stack height rule, and dual, hardwired UL 2034 certified carbon monoxide detectors with battery backup. When you respect the engineering, master the fluid dynamics, and build in harmony with the earth, you create a home that is truly built to endure.